Okay, so next up we've got our belts and we got our chains. So primary benefit of these is that we are able to allow fairly wide separation between the shafts using these flexible elements to transmit the power. It means that you're not as constrained in where you're placing your components. It can help to isolate your vibration. Downside, typically low power transmission situations. If you're talking higher power stuff, then some sort of gears might be more suitable. So if you need to offset that, then you could perhaps accomplish that by a pair of bevel gears, perhaps. But the manner in which they work, you got the tight, you've got your driven your driven, your driven element on the right here. You've got your driving element here. So as we got a tight side and a slack side. So basically, you got the slack side goes over to the driven element, and it starts to stretch out as it gets kind of pulled over. So then it's nice and it's all stretched out on the tight side, and then it hits the driving, and then as it hits the driving, it starts to shrink, basically as the stretch gets reduced when when you transition from the tight side down to the slack side. So those have two different tensions, P1 and P2. P1 is the higher of the two tensions, and we're able to transmit a certain amount of torque due to that. So again, like gears, we're going to have different torques based upon having the different radiuses for the sheaves that we're using here. So the torque will be based upon the difference between the two tensions and the radius of the element we're looking with. And we've got this. We've also got a limit on basically the maximum ratio between those two sides. So basically, the P1 divided by the P2, the maximum ratio there is e to the f phi. So where f is just the coefficient of friction between the driving element. The coefficient of friction between the belt and the sheaves in question. So based upon the materials that we're working with, and then this phi is just the angular coverage. So for example, for the driving element, the angle would be measured based upon the point of contact here and this point of contact here. So it's this arc here. And the driven element, we're talking a larger kind of area there, or a larger arc. So typically speaking, the driving element is going to be the limiting factor here, because that's going to have the larger phi, sorry, the smaller phi. So that's going to result in a smaller tension ratio. So we're going to if any slipping is going to occur, it is likely to be occurring on the driving side rather than the driven side. And that results in that results in a limit upon the maximum tension that we can get available, basically. So we're also going to need to apply some amount of initial tightening. So we're not starting out with zero tension on either side before we start rotating. It's good. We need this thing to be relatively tight in order to basically generate the friction to start with that gets this thing moving and starts us to start transmitting our power. So a typical initial tensioning that is used is just going to be the average of the two tensions. So just average those two out. And yeah, that'll get your initial tensioning. So control of said tensioning is also going to be fairly important. So what we do want to ensure is that we're able to adjust it as needed. So there's a few ways you could do that. One would be some sort of manual adjustment. So essentially, if you notice that it's starting to slip, then you can adjust the position of the motor here, kind of push it a bit to the side, and that'll account for any of the loosening that has happened over time. So loosening, creep can occur, especially for high temperature operations. So essentially, creep is the phenomenon where you get a non-constant strain over time with constant stress. So essentially, you're just pulling on it at the same amount, and it slowly stretches out. And then that stretching that occurs is permanent deformation. So you can adjust it manually, or adjust it using using a nut like that. We could have, say, like a pivoted overhung motor where it's free to rotate about this pivot here, and then basically the weight of the motor is going to cause it to want to rotate about that, and basically it's going to want to rotate this way, but it's going to be restrained by the belt, so you can kind of automatically have the right weight. We can also have a weighted idler pulley, where basically we've got this another sheave here that isn't really doing anything other than adjusting the tension, basically. So we can adjust that to tension by changing the weight, not just the amount of the weight, but also the position of the weight. So that the idler pulley is mounted on the pivot, whereas the driven pulley with its motor doesn't need to be. So when we're talking particularly high speeds, we also need to start taking inertial effects into account. So basically, we got our centrifugal forces that are generated. So as if we have a belt coming around here at a particularly high speed, in order to cause it to want to turn around the sheave here, we're going to have to apply additional force to it. So basically, we're generating some centrifugal forces that arise, and that can be calculated based upon this mass per unit length value times the velocity squared. So again, because it's a velocity squared term, we're really only worried about this for high speed belts. Obviously, it's still there for lower speed belts. It's just negligible. So when that occurs, then basically what happens is we're generating. We need to apply additional force on both sides. So we're adding additional tension to both the tight and the slack sides when we do this. So that and because this is going to be causing the belt to kind of want to lift away from the sheave, we're reducing the normal force there. So we're reducing the contact force, so we're reducing the friction. So that friction gets changed, our friction relationship here gets affected. So basically the ratio of the P1 to P2 that we could attain also gets changed when we're working at particularly high speeds. I would like to point out that because it gets added to both sides, our torque doesn't change. It's still going to be P1 minus P2 times R, because realistically what's actually happening is we got P1 plus PC minus P2 plus PC times R. These two PCs here, they both cancel out, so they go away. So the torque doesn't get changed when we're talking particularly high speeds due to the centrifugal force, but the friction does. So the ratio here is affected. It's also going to affect the initial tensioning that you're. Supposed to be the eraser. It's also going to affect the initial tensioning that you're going to want to do, because basically you need to apply a bit more tension in order to basically overcome that in order to overcome that tendency to kind of pull away. So it needs to be, you need to start out a bit tighter, and you're going to end up tighter. So your P1 that you eventually end up calculating is going to be a fair bit higher. Sorry, your tension in the tight side is going to be a fair bit higher. It's going to be that P1 plus PC. Here down here we'll have P2 plus PC. So this value here is going to be what we're going to be using for our failure criteria. So again, looking at some values that we might see for like leather, polyamide, urethane belts, some flat and round belt materials. These are given kind of a specified number of plies here, or these have certain kind of size criterias, so on and so forth. And then each of them, you're going to have certain thicknesses available, certain thicknesses for these flat belts, these urethane belts down here. These are round ones. Minimum pulley diameters that you're going to want to be using, pulley or sheave diameters. And then here's our limiting factor in terms of allowable tension per unit width. So basically, we can make these things wider if we need to in order to increase the strength, and that'll come with a specific weight in terms of this here is given in terms of pounds per inch cubed. So per unit volume. Obviously, you need to multiply that by the cross-sectional area in order to get the mass per unit length that we talked about here. And then you're going to have different coefficients of friction as well for the different materials. So two different types of polyamides, the A's and the F's here are given with 0.5 and 0.8. 0.4 is a reasonable coefficient of friction for leather on steel. 0.7, a reasonable coefficient of friction used for urethane on steel. We also got V-belts. So V-belts, when you're looking at them, you've got, when you're looking at the cross-section, you typically have, it's formed like a V, and you're typically going to be having some sort of metal reinforcements inside there, typically on the located closer to the top than the bottom. And yeah, various cross sections available. So the point of the V belt is that basically when you shove it into the V groove in the sheave, and you know, pull on it, then basically uh, you're increasing uh, the normal force uh, between the surfaces it's resting upon. So you know it's touching this surface here, and then you know it's tightened. So as it kind of gets wedged in there, we got more normal force, which means that we've got more what you might call it. More friction basically. So it changes our friction relationship. If effectively what it actually does is it changes our effective coefficient of friction. So our coefficient of friction becomes F, the normal coefficient of the usual coefficient of friction divided by the sine beta, where beta is this angle here. And yeah, so we fit that into that relationship, and then obviously the P1 minus PC and the P2 minus PC there comes into play as well. So typically speaking, you're not worried about slipping on the driven side. You're worried about slipping on the driving side. So oftentimes what you'll see they'll go to the effort of machining these grooves or casting sheaves with these grooves in them on the smaller side, and then on the on the other side, on the pulley side, you're going to have the bottom of the V belt just resting on the surface without necessarily needing an EV groove, because it's not going to slip on this side. It might otherwise slip on this side, so we're going to use the V belt to ensure that we're not slipping on the smaller side. So we'll cover the example later. Another thing to keep in mind, and I'm not going to go into too much detail about these, but we've also got timing belts. So basically, belts that have essentially tiny little little plastic gear teeth built into them. So you're meshing with sheaves or pulleys that have teeth in them as well. So because of the fact that we have these teeth built in, we're not really at all worried about slipping. You know, the action of the teeth fitting into the gaps on the on your sheave is what ensures that that there's no slippage. So these are often used, like I said, for timing. So we're ensuring that you know, we can kind of rotate and then and ensure that stuff's rotating kind of at the same rate. And yeah, generally speaking, your power capacity is gonna be limited based upon the number of teeth that are engaging. So a typical value that kind of gets thrown out there is that as long as you have at least 5 teeth that kind of engage with any particular uh, any of your any of the elements it's connecting to, then you can be reasonably assured that you can get your maximum power load there. Next up, we've got roller chains. So I'm sure everyone's seen a roller chain like this on a bicycle. So essentially, you've got these rollers in the center here. Those are what mesh with the sprocket, and then of course over here you can see kind of the links that are there to basically hold all the rollers together. So as this thing rotates, the rollers kind of mesh with the teeth on the sprockets. So one thing you'll see with the roller chains is basically if you look at the position of the roller when it first kind of comes into full contact with the sprocket versus the position when it is kind of at the top of its rotation there, it gets pushed up a little bit. So effectively, you get a change in the effective radius there. So if you have that change in the effective radius, then realistically what's going on here is you're also getting a change in the in basically the effective speed. So if this thing's rotating at a constant velocity, at a constant rotational speed, then the chain itself that's being driven, it's going to be seeing changes in its velocity as it rotates around. So that is basically a function, and the degree to which that happens is going to be a function of the number of teeth. So you get a certain amount of speed variation in the chain based upon the number of teeth. So if we're talking like only five teeth on the sprocket, then it could be up to 20%. Or as if we're talking 30 or so, we're talking, well, that looks to me to be down about 1. So drops down dramatically as you start to increase. So that's why you're going to have tendency to see relatively fair number of minimum number of teeth on your sprockets, which will also affect, of course, the size of the chain being used. And the other thing is, if you're using multiple strands, because you need to, because basically the amount of power that you're going to transmit would be causing forces that would be higher than what the chains could do on their own. Unfortunately, the multiple chains don't necessarily share the load completely evenly, so you need to take your load rating for like the one number of strands, and then you don't multiply it by the number of strands, you multiply it by this factor here too. So if you're using 5 strands, you take the load rating of the individual strand and you multiply it by 3.9, and that'll give you your load rating in terms of pounds or newtons of force that the strands can accommodate.